Hello everyone, welcome to the 7th lecture on reinforcement learning. And today we're going to be looking at function approximation. So in this lecture I'm going to be introducing what function approximation is. Essentially this allows us to solve much more challenging reinforcement learning problems, like the kind of problems you've got in your coursework or the kind of problems where you see all the exciting advances in deep learning and reinforcement learning coming together, AlphaStar, AlphaGo and so on. So I'll start by just defining function approximation and discussing the kind of challenges with it. In other words, basically why it's not straightforward to just start using deep neural networks on top of the current theory that we've been developing so far. Then we're going to look at a naive application of the theory, basically just replacing our value function with something like a deep neural network and training this with stochastic gradient descent and seeing what happens. Then we'll discuss the convergence implications of doing this, and basically just as a hint, it can fail catastrophically if you just try it out of the box. But lastly, we're going to see that there's a few neat little tricks that make this actually work quite well in practice. And by the end of today's lecture, you should be in quite a good position to research and investigate new state-of-the-art papers to make good progress in your coursework. So you might be thinking, finally, we get to tie together all of this stuff we've been doing now with the deep learning content, and you should have a good idea of where to go from here. Okay, so basically we're just going to be scaling up reinforcement learning to solve much more realistic and natural problems rather than just these toy examples as we've been looking at so far. So the techniques today will help you connect the knowledge you've been learning in deep learning to the knowledge you've been accumulating up to this point in reinforcement learning. And there's really one central idea in today's lecture, which is that we'll be using function approximators to estimate the value function and the action value function. So function approximators can just be things like simple linear functions, or they can be nonlinear functions like you would get in, say, deep neural networks. So previously, up to this point, we've been storing the value function in a very large table, like this huge NumPy array at the beginning of most of the algorithms you've seen. We've had this massive NumPy array, this big table containing all of the states and the actions, if it was the action value function, this Q function. And this was stored for all of the states and all of the actions that you would get. But that's just really, practically speaking, not scalable to large problems. So consider the game of backgammon. That has actually 10 to the 20 states. And the game Go has 10 to the power of 170 states. So it's just, you can't really store that in memory. And we also even have continuous action spaces, which have an infinite number of action states. Such as if we're controlling like a real robot, we have some actuators where you can give some real value for your voltage to them, which can be your action. So your action can be any kind of voltage, analog voltage signal, 1.7392 volts or something, and that would change the actuator. So you have this infinite space of possible actions you can take, and you can't possibly expand out all of those possible actions. So we really need to approximate these very large value tables, and we know that deep learning is quite good at this. You've seen in the deep learning course that you can sample from continuous latent spaces which truly learn the distribution of the data. And they can also generalize very well to unseen observations. They can truly learn the full continuous data distribution with just a finite number of observations. However, this approach does actually have several important implications that we'll be covering today. So here's an example where we've just basically said, before we sampled the actions with the colon from our Q table, and we got that set of actions. But now we're going to be using a deep neural network conditional on the states and also maybe the parameters of the neural network to get our action distribution. And we can parameterize this such as to learn a continuous distribution, or we can have some categorical distribution over the actions here. So to just make this formal, we can say that there are too many states or actions to fit into memory, and we can't possibly iterate through all of these. And if you remember, we had those outer loops through all of the states in our algorithms before. We had those big outer loops which went through every state, and we can't possibly do that. So I've got 3 example games here. We've got The Legend of Zelda, Final Fantasy VII, and a Pokemon game. And I don't know if you've ever played a long game like The Legend of Zelda. The Wind Waker or Ocarina of Time is shown here. But basically you can move on your analog control stick, Link, who's the main character, a forest boy around, and his movement is very, very smooth in the in this game world. There's thousands of states you can make just within a few frames just by smoothly moving Link around to play the game. So it's almost like we have these continuous action states with an analog controller. And after just a few minutes of play, there are many millions of potential states. So what we instead do, if we look at the equation here, is we build an estimator for V. We estimate the value function for that policy. So we say V pi is our value function, and we give it a state, and it tells us the value of being in that state. It tells us how good it is to get the sword at the beginning, or how bad it is to get hit by an enemy, and we estimate it with some function which has some weights, some parameters, and we say this V hat is our function estimator. Or for control, if you remember, we need the action value function. So in this case, we would have a state action pair, our Q pi, which would tell us, for example, if we're in the state next to a cliff and we're just about to take the action to jump off that cliff, we're pressing the jump button and moving in direction to fall off the cliff. And what is the value of that state action pair? And again, we can estimate that with something like a big linear function or a deep neural network, which is just to say that given as inputs the state and the action and the parameters, we estimate the Q value function, the action value function. So in any state, we run it through our function approximator parameterized by some weights, which gives us an estimate of the value function. Or in the case of the action value function, it just gives us the value for all of the states, for all of the actions. So it gives us a distribution over actions. So we might want like a softmax, effectively, in the last layer of our neural network. And then what we would do is we would update the parameters, we would update W of our function approximator using the kind of methods we've seen so far up to this point. And we'll update the weights using Monte Carlo methods or TD methods. And these methods will give us the targets that we'll then use to fit our function approximator to. So if you remember, by using TD methods or Monte Carlo methods, we get the targets for the value function, and we'll use these targets to fit our function approximator to. So it will give us a target for our loss function. So just looking at this diagram here, there are actually several ways or types of architecture you could use to achieve this. As you've been doing deep learning, I'm sure most of you are thinking of the function approximator should be something like a deep neural network. But in practice, it can be any kind of function approximator at all. So it could be linear combinations of features, it could be a decision tree, it could even be like a nearest neighbor approach or something similar. But for this course here, we're going to just restrict ourselves to differentiable function approximators, so deep neural networks and linear approximators. And in these cases, we can just update our weights by following the gradient. And if you've got lots of prior knowledge about the domain, you can actually incorporate all kinds of architectures or rules into it, and that would be valid for reinforcement learning. So in the first example at the top here, we're just showing state value approximation. Okay, so we feed our state, which in this case is the game The Legend of Zelda: Ocarina of Time. It could be like the state could be all of the inputs, like the pixels, or it could be some of the memory of the game if you happen to have access to that. But we feed the function to state, and then the function here, this network, estimates how good it is to be in that state here. And if you look closely, you'll see this is like where Link gets his first sword. So this is a very rewarding part of the game. If you're playing it and you reach this part of the game early on, you're like, yay, finally I've got a sword. I can now chop down and cut enemies up. So it's a good state to be in. But near that sword, if you play the game, there's actually this gigantic boulder which crushes you and if you get hit by it. So being in that state where you've got this boulder just about to smack into you, that's a much worse state to be in, because you're just about to lose your health, and maybe even you're about to die. So basically this is saying, given some state, what is the value of being in this state, conditional on the parameters of the deep neural network W. But when we do action value approximation, where we're estimating the Q values, there's actually two kind of main design choices we can choose, and the literature generally classifies these in the first case as being action in, and in the second case as being action out approximation. And so for action in this case I've shown the game Final Fantasy VII in the middle. You basically say, I'm in this state at the moment, I'm in this current state, and I'm considering this action here, I'm considering this choice, and they become your inputs for the function approximator, which basically then estimates how good it would be to take that action. But again, we have a function approximator such as a deep neural network, which is parameterized by W, and those and it receives those two inputs, and it spits out an estimate for the value of that state action pair. But for the case of action out here, we can see that sometimes it's more efficient to use a different form, and that depends very much on the context. So in this case here, with the game of Pokemon, you just have this single input state, and then what we want to do is we want to estimate the value of all the actions that you might take in this state. And this is actually more common in Atari, for example, where in one forward pass you might say, how good is it to move my joystick in every possible combination, so going left, right, up, down, and also on the Atari you have the fire button, and you've got the combinations of left plus the fire, right plus the fire, up plus the fire, and down plus the fire button. So you don't have many possible actions you can take. So what you can do is you can just get your network to output all the information required for this, and it gives an estimate of the value of all of those states. So that's the alternate form for this. Okay. So why is this non-straightforward? Well, consider you're playing a game like the Age of Empires here. This is like a strategy game. In this game you have to start basically controlling your units to pick up some of these valuable resources here, which you can then build a base, and somewhere else in the game you've got an enemy, and eventually the enemy might discover you and then start attacking you, and you've got to discover the enemy, send out scouts. It's a really, really cool game. But it starts out like a simple game, and things maybe start out going quite well, but suddenly as you sort of send out your units to explore the map, you discover there's a huge amount of maybe high valuable resources. Maybe there's like some of the best gold mines or whatever it is over here somewhere, or maybe you discover the enemy base is just right next to you. So when you find that out, when you discover that, this is going to dramatically change your value function, and it's going to completely change how you behave from then onwards. So all your efforts are now suddenly going to be in defenses or harvesting the high value resources as quickly as you possibly can before the enemy discovers them. So imagine just behind this square here there could be a massive dangerous energy base. Well, originally you might think there's lots of value to just send your units to pick up this gold or these resources here, but when you discover the energy base is right here and they've maybe got some watchtowers with archers on them, if you actually send your units over here, the value is going to be really, really bad, but you don't know that yet. So your value function is going to just completely change as you play the game. It's going to drastically change your value function, and all your strategies are going to have to change very quickly. So basically the rules of the game are non-stationary, and the algorithm convergence changes over time. And this is a big problem. We can't just naively apply our function approximators, because we need to somehow be smart in how we apply them. So we also need to allow for non-IID. If you remember, IID was independent and identically distributed data. And normally when we've been doing deep learning so far, we've been sampling our data from IID datasets. We've been taking a random sample from our dataset, and then we've been updating, following the gradient with respect to of some loss function with respect to our parameters. But this is definitely not IID. If you remember one of the earlier deep learning lectures where we talked about empirical risk minimization, having IID data assumes that all the data we receive is from the same underlying data sampling distribution. But in our case here, when we sample episodes of play, then the data we receive is going to be strongly correlated to the current trajectory that we're playing, the current game that we're playing in. So the initial moves I take is going to strongly influence how the data is being received. And there's going to be this game that I play right now, where we're receiving lots of data streaming into it. It's going to be very correlated to the specifics of that game. But if we played a different game and maybe we chose to move this way first, then the rewards, the values, and all of the dynamics of the game are going to be strongly correlated based on that way the game was played and sampled. Okay, so basically the rules of the game are non-stationary, and the algorithm changes over time. And we can't just apply our function approximators naively. We need to be smart in how we apply them. But in this case here, when we sample the episodes, the data we receive is strongly correlated to the current trajectory we're playing. So imagine you're moving around in some environment, and the data you receive is going to be all from it's all going to be from that same distribution for that specific game, and it's not going to be representative of all of the distributions, the distribution of all possible games, all possible ways you can play Age of Empires, and therefore there's this massive inherent bias when we need to smartly account for it. So we need to somehow use some tricks to make the data that we're receiving is more IID. It's more like the non-stationary data which we know deep neural networks work well in and can train well. Okay. So we said that we're going to replace our value function with a function approximator, but how do we actually train this? Well, naively, we're just going to use stochastic gradient descent, and we're going to treat it like a supervised learning problem. So basically, we're going to imagine that we have the true value function, or v pi, and this just tells us what our estimator should be. But later in a minute, we'll see how we can actually obtain that using the previous methods we've studied so far in the course. But imagine we've just got this perfect v pi we can directly use. We've got this supervisory signal, and then we can just treat the way we update our function approximator like a normal supervised learning problem. Or if you like, a simple regression problem where we minimize some squared differences between our estimate of the value function, our v hat, and minimize some squared difference to our v pi. So we've got some loss for, imagine we've got this ground truth which tells us what the value function should be. We're just going to basically regress with standard gradient descent to update our estimator to minimize the squared differences. Okay, so we're really just doing standard supervised learning, like training a classifier or in this case a regression network. So if we read the equation here, we're basically just saying we're updating our weights, our weight matrices for the neural network or the function approximator a little bit. So we're moving the new weight values a little bit in the negative. The little bit is alpha parameterized by alpha, or our learning rate effectively. So it's a little bit in the negative direction of the gradient of this squared differences between the ground truth value, our target, which we haven't yet said how we will compute, and just the prediction that the model currently makes. And we're going to take that gradient with respect to all of the parameters of our neural network. So we're going to back propagate through to compute this. This is from our prediction v hat. But on the second line here, I'm just going to show this common derivation of this, because there's lots of people like David Silver who always like to show this equivalence form. But basically, this is just the same thing, where instead we're saying our weights move in the direction of this error term, effectively times by the gradient. This is just application of the chain rule. Okay, so how do we compute v pi or st? So how do we actually get this? That's the real question. If we can get this ground truth of what our value function should be, then we can just treat this as a supervised learning problem, like training a classifier where we take our input states and we try to classify or predict what the value of the state should be. But we need to know that ground truth value function. So how do we get this this vpi, well, basically we need some way to compute it. We need some way to calculate vpi for our supervised learning approach. And basically, we're just going to use the same fundamental techniques that we've studied up to this point so far in the course. So we've got like several options available to us, and we're just going to substitute this vpi with whatever the target is. Okay, so what is this target? So in the case of Monte Carlo learning, we're going to use Monte Carlo methods, or we can use temporal difference methods. And this will give us this target estimate that we can use for our function approximator to learn. And then we're basically able to just use normal supervised learning to learn an estimate of that target. And this is all just very simple substitution now. We can just copy and paste the way we derived the value function in the previous 2 lectures to actually achieve this goal. So for example, in the case of Monte Carlo learning, we know that we can get an unbiased estimate of the return directly from experience of play. So in the case of Monte Carlo learning, the target vpi is just going to be the return. It's just going to be gt. So if we substitute that into the equation from the previous slide, we can now say that we update our weights a little bit by alpha in the negative direction of the gradient of the square differences between our prediction, this v hat, and the return, which is estimated with a Monte Carlo method. And similarly, in the case of TD learning, we're going to use a different estimator for our vpi, so all of this part in red here, which is our estimate. And if you remember, the TD target from the previous lectures was just equivalent to the immediate reward plus the discounted value of being in the next state. And well, how do you get that? Well, we can simply query our function estimator at the next state, and we can do TD learning this way. So we just query our actual value function in the next state, and this gives us this target here. And the same thing also happens for TD lambda. So it's basically the same idea, using TD lambda, the lambda return, which interpolates between TD0 and Monte Carlo learning, as was calculated in the previous lecture. So one question you may be asking by looking at these substitutions is, you may say, well, why don't we just calculate the gradient of our targets? Could we use this information as well? Like, could we compute the gradient of these things as well and move in that direction as well? So that we could actually do that, and we would have 2 sets of gradients. Surely, like averaging them or adding them up or something would be even better. But the answer is actually no, you can't do this. We don't take the gradient of both the target and the gradient of the function approximator. We only use the gradients of our function approximator. If you were to actually use both gradients, you can basically end up cheating, and it can converge to the wrong answer. It's a bit like if you let too much signal through in an adversarial model, it no longer becomes adversarial. And you need to kind of follow the flow of the information to go one way or later in time. So just to clarify this, we want to calculate the gradients of our function approximator, and even though we could calculate the gradients of our targets, say with TD0, we don't actually want to do this or to use these. Okay, so that all tells us how to use function approximation for prediction, so we can use it to basically estimate the value function. But do you remember that what we really want to do is learn the optimal behavior, so we can do control, and we can have our agents learn the best way to play the game. And to do that, if you remember, we need the action value function, which previously we had as just this big NumPy array of all the states in the actions, that big NumPy array of the state action pairs. But basically now we can use this big function approximator, which will parameterize with the weights w, and then you can, if you read the equations, you'll see that we can do basically the very same thing here using Q. So we define the error now. We move this error here as the square differences between our estimated Q values here, our Q hat, and the ground truth q pi here. And then we do stochastic gradient descent by updating our function weights a little bit. So we take our function weights and we do stochastic gradient descent. So we move them a little bit by alpha in the negative direction of the gradient of this big error function, this loss here. And we do that all with respect to our parameters. So we back propagate through to get those gradients. And then we can update our parameters accordingly. And again, that's just showing the common derivation that several people like to use in the literature. They like this bit where you see it multiply through. You can just see that as the equivalence here. And then the big question then becomes, how do we compute this q pi, this ground truth target of the action value function? Well, we can end up just substituting it. So this again is basically the exact same thing, just like before. How do we compute our estimator of the ground truth q values, just q pi, and just like in the previous slides, we can do the exact same thing again, which is to substitute our q pi with estimates using the approaches we've covered so far. And I'm not going to dwell on all of this too long, but you can see that for Monte Carlo learning, we can just substitute our estimate of the q value with the return, but now we use our function approximator q hat of the state action pair, which is shown in red, and basically this is just all expanded through. We've just replaced now all of the value functions with our the estimated of the value functions with our estimate of the q value functions, and all of these substitutions are basically the same. We minimize the squared differences between them basically. So also for TD0, we can use that one-step TD target, which was the immediate reward, plus the discounted action value function for the next state, which is again a query of it. You have to query the function, the estimator at that next state. So this is just calling our deep neural network at the action value function of the next state to get our TD target. And lastly, we can use the lambda return here. Okay, so all of these are the exact same as before, but we just use Q instead of V. And once we have Q, we can do the max over our actions without needing an environment model that tells us all the transition dynamics. And basically that's all the essential theory of function approximation. So that's pretty much most of today's lecture. But the real question now is, does this actually work? How effective is this? So do these algorithms converge? Up to this point, we've always had these really nice convergence guarantees with everything. And we want to know now if we can update our parameters of our function approximator in a stable way which converges to a fixed point that's close to the optimal parameter vector. So can we just chuck this in and leave it running and know we've got these nice guarantees, so we don't need to worry too much? Well, especially for control, in practice we find that these algorithms can be quite unstable. And theoretically speaking, all of those nice convergence guarantees are now unfortunately lost. And in this table here, we show that we can have like all the nice theoretical guarantees when we use tabular methods, when we have those big Q tables which do everything. And if you can store everything in a big table and just iterate over it, you've got all of those nice theoretical guarantees. And also we can make it work for simple linear function approximators. I won't really be going into these as they're not actually very powerful in practice. But basically you can add an extra term to Q-learning in the case of linear functions to make the approximation actually guarantee convergence. But what we really care about is non-linear function approximators like big deep neural networks which have the ReLU activations in them, or the non-linearities are introduced, which allow you to get much more interesting learning occurring, generalization. But sadly for non-linear function approximation, we lose all of these nice convergence guarantees. In particular, there's something that David Silver and a few others like to call this kind of chattering effect, which basically means when you do your function approximation step, there's no guarantee that you're actually improving your policy. So you might take an epsilon greedy step, but we no longer have a guarantee that this is actually making some progress anymore. And you can actually make progress for several steps, but then your gradients can become wrong, and then you suddenly undo all of those changes again. So it's like you end up chattering around. You make progress, and then you take a wrong step in your gradient deception, and then you undo it all, and then you converge again, and you undo it, and you kind of get this bouncing effect where you sort of end up just chattering around the optimal policy, or you end up chattering around the optimal action value function. So the tick in these brackets here basically means you get the tick with brackets here means you get convergence, but with a lot of chattering. Whereas a cross in this table here basically means you can actually get catastrophic divergences and explosions in your gradients. So we really need to do something about it. This would be like the case where you start following your gradients and your gradients start going wrong, and for whatever reason they get worse and worse and worse, and you end up getting this catastrophic divergence, and your loss just kind of explodes off into infinities, and you end up with nans everywhere, and everything just goes terrible. Okay, so we really need to fix this somehow and make these algorithms more stable. Okay, so just to recap, we've been following our gradient, and we've been updating our weights a little bit in the negative direction of our gradient according to our learning paradigm. And this is all a bit like having a batch size of 1 and then updating the weights based on some observed stream of experience where all the subsequent data is strongly correlated. That's kind of how you can imagine it. You can imagine like some deep learning problem where you've got a batch size of 1 and then all of your data that you're training on is all very, very similar. And that doesn't actually tend to work very well. If you think of that in terms of the optimization landscape, you're basically just going to start moving towards some specific point in the optimization space. And you're going to sort of go down this valley deep into this point in the optimization space. And then when you've reached that, you're going to start somewhere completely different and then just start going into a different valley somewhere in the solution space. And this means that if you ever encounter a rare experience, like say you find this extremely useful shortcut to go somewhere, then as you play another game, you're immediately going to forget that very useful shortcut. You're immediately going to forget about it, and you're just going to start some new journey. Rather than trying to like consider the full optimization space and find really good solutions which cover all of it, you're just going to just fall down these valleys and never really learn to generalize to the whole distribution of the data. So experience replay is a technique that addresses these issues. And basically we have a replay buffer where each element in the buffer contains a sample of a previous state, the action that was taken, and the reward, and then the next state. So it's like a mini buffer containing our past experiences that we ever played. And every time we train and we take an action, every time we sample from our environment, we basically just push this tuple effectively into some buffer, into our experience replay buffer. And then when we actually do our training, instead of sampling from the direct experiences, we now just sample from our replay buffer. So it's like we create our own data set which contains many of the experiences. We just uniformly sample, I should say, a batch of, say, n experiences from this replay buffer, and we train on this. And that this buffer can be quite large. It can have, say, the past 50,000 or so experiences, and the size of the buffer will obviously impact the convergence and balance out these stability issues. So having this buffer of all of our previous experiences that we can sample from breaks up all of those temporal correlations, those highly correlated trajectories, and it mixes more and less recent experience for the updates. So this also means our rare experiences will get reused from that buffer in more than just a single update. And there's very basic advances on this, but this actually really does work quite well. It tends to sort of make the data more IID than just having these highly correlated trajectories by pushing our experiences into a replay buffer and then sampling from this instead of just directly training on our experiences. And we can also pull out nice batches of these experiences. So there's another variant on this, which is called prioritized replay. And this is a more recent paper. You can read about it and see it does and how well it works in specific Atari games. But it's the same as experience replay, but the experiences within the replay buffer are, instead of sampled uniformly, we actually weight them and sample them based on some importance heuristic. So we sample them based on their importance. It's a bit like saying some experiences I've had in the past are much more important than others. Maybe you played some really bad games which just were gibberish, but you had these really, really good games where you did really well. Can we sample these really good states and just train from those? Will that help? That's the main idea. So we're going to do a non-uniform sampling, which is actually akin to importance sampling, the importance sampling algorithm. If you remember, we briefly discussed that in the Monte Carlo methods lecture. So how specifically are the experiences in that buffer weighted? Well, the paper proposes to use the magnitude of the temporal difference error for that weighting process. And this weighting introduces some kind of bias, and naively you can imagine the learning getting stuck on only the very most important memories. So we solve it stochastically in the importance sampling process. We still make sure all of the experiences can be sampled from. We want it to still be like a Monte Carlo estimate where we can still sample from all of the experiences with some probability greater than 0, but we kind of skew those probabilities towards the more important probabilities of experience. Basically, from an implementation perspective, instead of doing random dot sample, which is a uniform sampling approach, we would use like numpy.random.choice, which allows you to additionally manually specify the probability weight for which every element in that buffer is sampled. So you can say, I want to sample this element with some probability and this other element with a different probability, and then numpy.random.choice will just sample, like say from a multinomial distribution to sample all of the different experiences differently. So that probability is just skewed by some exponential, which is renormalized to ensure that it integrates to 1, a bit like how the softmax works. And you can actually look at the paper to see it more clearly, or you can study the implementation. Okay, so we're just going to have a look at some code which does this. And this code is a deep Q-learning network, which is very similar to what you've got as the starter code in your Atari coursework. And basically we just import Torch and we import the gym environment. But the first thing we do is we define this replay buffer. And the replay buffer just takes our experiences that we sample from the environment. So every time you're playing a game or training the agent, we're just going to take that experience of the state, the action we took, the reward we got under that action, and the next state that we transition to. And we're going to just push that all into some buffer as well as this terminating condition, whether that was actually a terminating state. And then we're going to push all of that into this big buffer, which then we can sample from uniformly, which is where we just basically sample a batch of experiences from this buffer with some uniform random sampling, so there's no weighting or anything in this case here. And we're going to then train on that mini batch of experiences. And there's our batch there, and we just zip that all together, so we make this nice little mini batch that we can train on. And the replay buffer really just, every time we get new experiences, we're just going to add them into this buffer. But when the buffer reaches some max capacity, some max size, we just get rid of the oldest experiences. And the capacity in this case is usually something like 1,000 or 10,000. I have to see where that's defined. There it is. It's defined to be a 1,000 here. That's got quite a small one. In practice, you might want 10,000 or even 100,000, depending on how IID you want to try and make the data, which depends on the stability. So that's definitely a hyperparameter to play around with based on the environment, based on the size of the states and the sparsity and so on. How correlated the trajectories are. So the network is just a deep Q network, which has this epsilon greedy strategy. So it's just got a bunch of linear layers, in this case very naive, with some nonlinearities between them. Where you've got your input states and your output actions. And then the epsilon greedy strategy is basically where you run it through with your current state. So you input your state and you output these Q values. and then you take the max Q, the maximum action, the maximum Q value, which tells you, which action is the best one to take, and that's your greedy strategy. Otherwise, with some epsilon, you'd have your random sampling of the action, so that's your epsilon greedy there. The rest this is just your TD loss, which is your reward, your discounted reward plus the discounted action value of the next state, and this just backpropagates through this batch here, and so on. So also we can have the prioritized replay buffer, which is the same again, but this time the definition of the replay buffer is a little bit more complicated because we somehow need to wait. When we sample, we need to weight the experiences based on their importance. And how do we do that? Well, instead of having that random.sample, we now have mp.random.choice, and this lets us additionally specify the probabilities from which we wish to sample our experiences from. And these probabilities are basically just weighted by some exponential and then renormalized such they are actual valid probabilities. Similarly here, so we can get this nice distribution over all of our experiences, and then we sample accordingly. So we get this basically just gives us a nice weighted batch of samples weighted by some importance heuristic, which you've got some control over in the betas here, to sort of how much you skew the distribution, and the rest is basically the same. Okay, so putting this all together, we sample an action from our epsilon greedy policy with this GLE approach, or greedy at the limit of infinite exploration. So if you remember, we just anneal that epsilon parameter down in such a way that it starts off by doing lots of exploration, picking lots of random actions, just sort of randomly wandering around drunkenly, but eventually it converges at the limit to this optimal action value, which has no exploration, but it exploits the environment. We then store that state, the chosen action, the reward from the environment, and the next state, so that SA, then the R plus 1, and the next action. So we store all of that into our experience replay buffer. So that's what we saw, where we basically pushed everything into our replay buffer. We get all of that from the environment, and we push that into our buffer here, which we'll say is our sort of data set, if you like, D. And then to train, we randomly sample these experiences from our experience replay buffer, from our D. So we sample uniformly in this case, or by some distribution, from a batch of data. And then what we do is we follow the negative direction of the gradient from our Q network towards our Q targets. And the Q targets are just the same, but with a max there, effectively, instead. And there's a trick you can actually do here, sometimes called, it's called double Q learning. And basically what you do is you freeze the network that you do the max over for some number of iterations. And then every sort of 100 steps of training, you swap over again. And you can look up the double Q learning paper if you're interested, but pay attention to the gains it gives, because sometimes it can be effective and other times it's maybe not so effective. So it's really worth considering whether you actually use these kind of regularization tricks which impact the sampling. Okay, so in summary, function approximation can work, but it does require additional tricks to make it more stable. And the main problems relate to the non-stationary, non-IID data, which causes those kind of chattering issues where the gradients kind of point the wrong way and you end up following the wrong way. And it can even result in catastrophic failure with gradient explosions and just going crazily off. But experience replay really greatly helps out here because it slows down the convergence and it introduces, and it can introduce biases and instabilities of its own. But generally speaking, it does make the data more IID. And prioritized experience replay with importance sampling can often offer further control over these kind of biases that are introduced, but it can introduce another element of tuning or your parameters of how you skew the importance of your experiences between a uniform distribution and the heavily skewed softmax distribution, where you put high weighting to the most important So it's more like a categorical distribution. But really try to think and imagine the effect of populating that experience replay buffer. So what happens if it's too short? What happens if it's too large or initialized poorly? What happens if your learning rates are all too large or too small? Try to build up some intuition with respect to like the size and distribution of the experiences and how correlated they are. So if you've got highly correlated trajectories with a game where it's hard to find the actual correct path, then you need to really think differently about how you would parameterize that replay buffer to capture those rare experiences, how important they might be to the game. So I would suggest you read recent papers and study the kind of implementations, and there's a link here you can click, and it's got lots of really cool extensions on this, which I strongly recommend you have a read through some of these. You've got papers and code to go along. That would be a good area for some self-study this week. And you can see I've started to introduce some tricks which greatly help here. And now in a 10 lecture course, I'm basically definitely unable to introduce all of the tricks and really go to the state of the art. So what I've focused on is rigorously introducing the very foundational theory. So now you should have these foundations available to read most of those papers and really apply it to what you know. The coursework there is really testing your ability to digest papers in a short space of time and apply these foundational topics which we've introduced up to this point. So you need to develop the skill of reading a paper quickly and reading the abstract and the key equations and linking it to the theory. And study the benchmark results also in the papers to gain intuition as to what tricks work well and under what circumstances they work well. And what method, you need to ask questions like, what method do you think will work better for gravitas, say? Will double Q learning be effective, or will prioritizing your replay buffer be effective? What do the paper results indicate in this case? Are there any more recent papers which are citing those papers with even better results, and so on? And as you read papers, you'll see that Gravatar actually scores extremely poorly for many of the benchmarks. So I'm definitely not expecting you to achieve a superhuman agent here. And also you may find that the current, it's very difficult to beat the state of the art without loads and loads of compute. So I'm not expecting you to have a superhuman agent which just hunts down everything and destroys Gravatar. It is as you'll see in the benchmarks, it's one of the hardest ones, but this will really test on how you understand the kind of concepts here we're starting to introduce and what regularization strategies work well. So you may also find in the coursework that the current seed performs particularly well in the baseline architecture, whereas you may develop a better approach which just has bad luck at the beginning and doesn't get enough training, doesn't seem to do well. So therefore you need to really carefully look at your average scores and the convergence. Don't just look at the best scores that you get, because there's a lot of variance in your results that you get. Make sure that you spend time to read new papers and see how well they do in similar cases to your hypothesis or any new experiments or ideas you might have. And the RL assignment will really test your capabilities, not only as a machine learning software engineer, but also your ability to write working code within a limited budget constraints, and you've got this very noisy, misleading ideas you can get. So often you'll think you're onto something with RL, and actually it's just an effect of some noise or some trajectory going down with highly correlated data, and you might think it's really worth learning to generalize, but actually it's just going down some rabbit hole, and it's just not IID or actually learning any well generalizing policy. So it will later start to diverge catastrophically and so on. So this is really going to stretch your grasp of the scientific method, because you have to be very careful of how you choose your experiments, taking into account the variance you get in your results, and it will also test how you select the papers, how you read, and how you go about this research. So you can't just try the first thing that pops into your head without developing some hypothesis here, and then you have to weigh up your options and within the set of competing hypotheses you have, and what gains can you reasonably expect to get from this trick. What evidence do you have to support it being worthwhile in the situations you're encountering, say within Gravatar? And then why is your algorithm failing, and how can you test this? You've got to have asked all these kind of scientific questions. So do make a comment at the bottom of what you've observed and tried at the bottom of your code. But remember, there's no perfect solution to this Gravatar assignment. So you're not graded on the amount of training, but rather the application of the theory and how well you've researched and developed an appropriate agent. Okay, well that concludes this lecture. That's it. I hope you have a good week.